and welcome everybody to my presentation on surface plasmon resonance as a student project for advanced solid-state physics. I want to tell you a little bit about general concepts, the optical properties and the applications of surface plasmon resonance. So for a short overview, today I want to tell about surface plasmon resonance, then I'm going to show you some facts about nanoshells, and in the end I'm going to show you applications of a specific type of nanoshells, silicon dioxide gold nanoshells. Okay, what is surface plasmon resonance? As you can see from the name, it's a resonance phenomena. So something gets excited by usually light waves, and then you get a resonance behavior. So by shining light on usually small metal particles, you induce charge waves, charge density waves in the surface electron density, and by this way you excite the whole electrons that are able to move, so usually the conduction band electrons of the particle. Then the light wave goes through and the now displaced electrons start to oscillate. So you get a confined oscillating electric dipole that's re-emitting light. That's a resonance then. What is the prerequisite for that? The particle has to be smaller than the incident wave, so smaller than the radiation wavelength, so you can really excite all. It's not about single electrons, but exciting all the electrons and displacing them compared to the ionic cluster, like you can see in the small sketch down there. And for most applications, the particles are in the nanometer range, so you can think about it's like if the particle is in the range of visible light to UV, you need nanometer particles. What defines the energy of surface plasmon resonance? There are some parameters of the usually spherical particles that affect that. That's in general the size and the shape. And then it's very surface electron density sensitive. So if you change the dielectric constants, if you change the media, if you change the surface in any way, you get a different type of resonance and different resonant frequencies. And because you have small particles, the smaller the particle you get also quantum dot phenomena. So you get really precise wavelengths for re-emission. And as you can see in the sketch down there, the smaller the particle gets, the more you shift into the blue. So with a bigger particle, you get more into the red. You get an increasing excitation wavelength for the surface plasmon resonance, and the peak also broadens a bit. It's really sharp at low wavelength, small wavelengths, and really it broadens up when you go into the red regime or infrared. So how can you use that for a technical application? For example, nanoshells. Nanoshells are just a dielectric core that's covered with a metal shell since you need the free electrons. And they're quite easy to fabricate and they're easily tunable. You can, when you fabricate them, you can the layer thicknesses of the two materials, you can engineer them, and you can choose the relative thickness, and that's really important for the resonance. Like you can see the extinction over the wavelength on the right side, and just by keeping the same 60 nanometer core and changing the shell radius from 20 to 5 nanometers, you shift about 300 nanometers in the main extinction peak. And of course, so you can engineer, by changing those values, you can engineer first of all the resonant wavelength where surface plasmon resonance happens, and the ratio between absorption and scattering depending on what you want for your application, if you want more of absorption or scattering. So why would you use nanoshells for medical applications? There are many reasons for that, especially since you have the particle and you can choose just by the intensity of the light if you want to heat up the particle, if you want to use it for imaging or whatever. So the main applications are just enhanced imaging. If you use infrared, you can easily penetrate skin really deep through the skin, and you have a powerful tool for micrometer resolution live imaging. Then you can heat the particles by high intensities, so you can just burn cells that you want to have burned, or you can coat the particle like it's shown down here. This light gray area is a coating, it's a polymer around the particle. It's easy to apply, it doesn't change the resonance a lot, and that you can bring into targeting molecules, and then the body itself brings the nanoshell wherever you want it, and you can attach other things to it like a drug you want to deliver, and it's easy to put it there, and then you can even use the nanoshell to rupture a membrane by heating it up again. So there are many ways to engineer nanoshells for medical applications, and combining those makes them so interesting for medical applications. Okay, so now to go into more detail, we're going to talk about silicon dioxide gold nanoshells. Why are those important? Gold is a very well-known material, of course. It has the properties that the excitation wavelength is easily tunable from visible to near infrared, and infrared is really where the medical applications shine, because you need the skin penetration. Then gold is non-toxic for the body. You can use this coating I described before and add functional groups for specific purposes. And those nanoshells, gold nanoshells, are affected by something called EPR, so enhanced permeability and retention. And that is something that's really important for cancer treatment, for example. It's just a cell with a really high metabolism tends to accumulate particles in the size of nanoshells and keep them there. So you can accumulate cells in cancer tissue really easily, just without any effort. So the usual design for nanoshells is about, if you take about 100 nanometer core and a 10 nanometer gold shell, you get an absorption peak at 800 nanometers. That's about what we want to have. And down here you see how they are created. So you just have the glass core, and the gold grows on it. So as an example for the results, just put those nanoshells into tissue you want to test. Of course, that's made in a lab and not in a human body. And then you irradiate them by a laser of a certain frequency with a certain intensity for a certain time, and check how many cells are affected. And here we have cancer cells in the top row, and then the bottom row we have skin cells. And then you see different types of nanoshells, from targeted nanoshells, from just the coated nanoshells with this polymer I talked about, and bare nanoshells. So bare nanoshells are irradiated, and any cell they kind of touch gets a heat transfer and is destroyed. So you can see the destroyed red cells, skin cells, and cancer cells is alike, so no difference. If you coat them, they keep a distance and they don't kill the cells anymore. So no kills for cancer cells, no dead cells for skin cells. And if you put a targeting molecule, the nanoshells specifically bond to the cells you want to target and only transfer their energy when they're heated up by the resonance to those. So you kill just the cancer cells that are prepared in the center, and nothing happens to the skin cells. So that's a really precise way to affect cancer cells, and there's a lot of research going on into this area and many other applications of those nanoshells. In the end, I want to thank you for your attention and leave you with this picture of a highly magnified nanoshell. And if you want to go further into the topic, here are the references where you can find a lot of information on those. Thanks.